Dziękuję. Dziękuję bardzo. Dzień dobry. Chciałbym podarzyć przykładem Gabriele i przedstawić się w języku polskim. Jeśli każdy rodzimy polski mówca mówi po angielsku, a każdy zagraniczny mówca mówi po polsku, zmaksymalizuje to nieefektywność. You understood sufficiently. Is Gabriel in the room? Gabriel Volpe? Hey, desafío aceptado. Gracias. So, welcome everybody. Enough foreign languages. I'm going to talk today about 11 little life-enhancing libraries. I'm only talking about 11 of them because it happens to be alliterative. But they're all microlibraries. These are small, self-contained libraries that are single-purpose. They do one task, and in theory, they do it well. That's the intention. And if you want to use them, you can use them a la carte. You can pick these libraries, and they won't interact too heavily with anything else in your system. They don't pull in lots of dependencies. They don't have this large surface area of potential conflicts in big dependency trees that might cause problems. And they should be very easy to combine and to compose. They're modular. You may have noticed recently I've been working on a build tool. I'm not going to talk about that today, but I'll show you this little demo just because I think it's quite cool. But if you look at Fury building a project of mine, this is building my website, you'll see there are lots of dependencies, and they're all building, or most of them are building very fast. These ones in green have already finished. These are all microlibraries, and I use them to my advantage to make it much easier to write Fury. They have been, in general, these libraries have been an enabler for Fury to work as well as it does. And in only, Fury has about 5,000 lines of code and a few microlibraries. So I'm going to look at 11 of these today. And each one I think is unique in its own way. I've tried to find some unique feature of Scalar or some unique usage of a macro to do something new that hasn't been done before. And I've ended up with many of these libraries, maybe because as soon as I discover an idea, I think, well, this deserves to be in a library by itself. I don't want several of these combined into a big project. And I would also like to encourage you to use them. So if you see a library, one of the 11 that I talk about today, and think, well, this could be useful in one of my projects, think about using it. And also think about contributing to it. I have a lot of things that I get involved with. I'm running Scalar World. I'm developing Fury. I do commercial training. All of these things take up my time, and I don't have as much time as I would like to work on the libraries, but they are really good for anybody who wants to contribute to Scalar, because the amount of code in each library is usually under about 500 lines of code. You can read the entire code of the library. It's not necessarily easy, but you can read it, you can understand broadly what is happening, and it becomes very easy and very accessible to anybody who's interested in contributing to those libraries. Development is usually driven by my most immediate needs. If I need something for Fury, that's when I go to the library and I add the feature that's necessary, or the type class instance. So I would like to bring them up to production quality so they're more generally usable to more people and to a wider audience. They need more testing, more documentation. These are all things that I can help people with, but I would love to get other people involved in and helping me. So the libraries, you may notice some similarity or consistency in the naming choices. Contextual, Adversaria, Caesura, Kaleidoscope, Mercato, Guillotine, Optometry, Honeycomb, Gastronomy, Mutatis, and Pyroclastic. I don't pick short names except for tools. What I'm going to do is I will spend 2 minutes, that's 120 seconds on each library, and I have a timer here that's going to make sure that after 2 minutes I won't talk any more about that particular library. I will move on. We're going to have 22 minutes. It's going to be fast. I'm not going to take questions. I'm just going to rush through it, and hopefully it will all make sense. Okay, ready to go. Let's talk about Contextual. Contextual is a library I started writing about 2 or 3 years ago. You may be familiar with interpolated strings. These are a little bit like literals for other types. So we can define an email address there. Now you all know my email address. You can send me messages. But it's prefixed with the identifier email, which means this will be parsed as an email. And what Contextual allows you to do is to define how that gets parsed. And it gets parsed at compile time. This would be a compile time failure if it wasn't a valid email address. That's something Contextual allows you to do without you writing a macro. We can do other things, decimals, binaries. All of these can be checked at compile time. And all you have to do to implement one of those verifiers is define an instance of this trait, specify what the return type is, so it might be an instance of an email address, and implement this check method. The out type is the successful value, so right of the successful value if it parses correctly. If it fails, then you specify what the error message should be as a string and an index into the string that points to the error. The compiler will point to that error for you. That's all you have to do. With that implementation, here's the implementation for email address. We have to do one more thing, which is to bind that using this. This is more or less boilerplate, this implicit class here. We bind that to the email identifier. So you can look at the code afterwards. We're going to press on. We can even support substitution. So here's a CSS example. If you wanted to substitute an alignment value or a color, Contextual will allow you to specify what types are valid in what holes. So these parts are known at compile time. These parts are known only at runtime. So Contextual has to work that out. And in order to do that, we need a slightly more complicated version called interpolator. We've run out of time. So let's move on to Caesura. Caesura is a library for working with CSV. Each of these has a little explanation as to where the name came from. So this is the definition. How many people work with CSV? I'm sorry, but I'm going to try and make your life easier. I'll show you how this works. We first will import Caesura, and then we can define a row. Unfortunately, I can't pronounce Krzysztof, so okay, it worked. So that's just a case class instance, that's just a CSV line, one line from a CSV file that contains quotes, nothing particularly exciting. CSV isn't exciting, really. We can then parse that, given a case class to parse it into, like person. We can parse that line simply by calling row.asPerson. So step 1, parse the string into a row. Step 2, parse it into a case class. And Caesura allows you to do that with complicated case class structures as long as it knows how to parse each element in there, strings, ints, and nested case classes. So it will flatten nested case classes, so these work as well. And we can go backwards. We can we can put that person into a row, step 1, and then we can serialize that to CSV. It's really simple. There's nothing exciting here, but it does work, and it is very generalized. And if you wanted to use tabs instead, tab separated values, you can do that too. There is the possibility to implement variations of this. CSV isn't well defined, nor is TSV, but you can extend a class and implement your own variations. And that's been provided by Hubert at Virtus Lab, so I'm grateful for that work. Time for adversaria. How many people use annotations in Scala or Java? These are the little things prefixed with an @ sign. We can define them. Most people will use existing definitions, but you can define them with case classes that extend static annotations. So we can define things like ID, unique, and table, which takes a parameter. So they can be parameterized, and they can then be attached as metadata to existing language constructs. So we can attach the table annotation to the case class company. So maybe this company is actually going to be relating to a table with a different name. It's not called company, it's called organization. And we can identify that the email field of this case class person is both unique, it's marked as unique, and it's marked as being an ID field. By the way, these can be used in a variety of different places. So to use it, we import it, we define that thing we saw on the previous slide, and then what Adversaria does is it allows you, by means of a type class, to get the annotations, the type metadata on that case class. And what that will give you back is a runtime list containing those annotations. So we know that the table is annotated. That table there is an instance of the case class. It begins with a lowercase letter by convention for an annotation. Same thing here with defining our person type. We use a different type class, find metadata, which will find the field that is marked with ID on the case class person. So what we want is email. It gives us back basically a lens that allows us to access email. And then we can apply that like so, and we find out that he's from Wenkawade. This is very fast. So let's. We're too late. We're going to have to go on to Kaleidoscope. There's nothing exciting on that slide anyway. So Kaleidoscope is probably one of the most useful libraries I've written, and it allows us to pattern match on regular expressions. We can define this case match here, and much like contextual interpolators, we can prefix a string that we're matching on with this little R character here, and then this will be interpreted with Kaleidoscope. And all this is doing is saying, does the string we're matching on, this name here, match a certain pattern? Does it have two words separated by a space, each starting with a capital letter and the remainder of the letters being purely alphabetic? If it does, then we'll return true. If it doesn't, then false. We could even extract stuff from that regular expression. We can use an identifier in this pattern to bind that capturing group there. Hopefully you can see what I'm highlighting. We bind that capturing group to the value first. First is now a string. Same thing with last. And we can extract these into a tuple of two strings. If we fail to match, then we're going to have to use something like no name. And if you're working with regular expressions, if you're working with strings, you probably want to, as fast as possible, you want to convert them into better typed data, more strongly typed data, with less that accommodates less possible variations. Move stuff out of strings as soon as possible. And Kaleidoscope's a really useful library for doing that, whether you're getting strings out of JSON, out of XML, out of user input. At the earliest opportunity, convert them into better types than string. I've got 7 seconds left, but let's add that to my discussion on Mercator. Mercator is a projection of it flattens. It's a flattening of the globe onto a single sheet of paper. We're talking about flat maps here. Have you ever wanted to write this code? If we have some sort of type constructor here, and we want a method which is generic over that type constructor, so it works for future or try or either or list, and we just want to do something simple like add one to that, that will not compile in Scala. The reason it won't compile is that the compiler doesn't know that m of int has a map method, or potentially a flat map method. What we can do is we can import Mercator, and any type m, any type constructor m that does define map and flat map will have a monadic instance generated automatically for it, and this will just compile. So it generates the type class on demand when you need it for any type for which it makes sense. And the rules for when it makes sense are the same for the rules that when you can use a for loop or for comprehension. What it creates, what the compiler constructs, or what Mercator constructs, is an instance of monadic for that particular monad type. Flat map and map get generated automatically from the definitions, and point, which will just create the simplest instance of that a wrapped instance of that value will get generated by looking at the companion object to try and find the most sensible implementation. We also get sequence and traverse. If you have, for example, a collection of your monad of A, sequence will convert that into a monad of a collection of A. Traverse is a more general version of that. I'm not going to explain that in the next 7 seconds. Who likes food? Gastronomy is about digesting stuff. Cryptographic hashes. We can import gastronomy, and lots of different types can now have a .digest method called on them. We call 42.digest. I can't speak English. And we can specify the cryptographic hash function we're going to use to make that digest. This happens to be the two-string representation, which is the base 64 representation of that immutable digest value. We can do the same thing with SHA1. It's a longer hash, of course. SHA256 is also available. We can also define more complicated structures. Here is a person that has two primitive values, but also we can have a group that contains a collection of case classes. And we can create some of those, we can put them in a single value, and then we can call .encode, or .digest on that. We get the MD5 digest, and then we can encode that, if we want, as whatever particular encoding scheme we want to represent that as. I'm choosing hex here. I could choose base 64 and SHA256, we get a different value back. If I knew that I was always using base 64, it's used globally throughout my code. If I'm always using SHA256, I don't need any other kind of hash, then I can just import these into scope. And the commands become simpler. I just call .digest and .encoded. And because these are implicits and because they're in scope, they become higher priority than the others that are available. So we don't need to specify as a type parameter. So this is very, very concise. I'm way ahead. I'm going to spend another 20 seconds on Honeycomb. Honeycomb is my approach to generating HTML. Now, HTML allows us, with Honeycomb, we can write some HTML, for example, a table like this. We can nest a t-body inside the table, tr inside t-body, th and td goes inside a tr. That all works fine. You'd expect it to generate some HTML code that will, when rendered in a browser, look like a table. That's all fine. We could even have a div containing an image which has an attribute. That's what an attribute looks like. That is all fine, nothing particularly surprising there. But what happens if we write this? Well, in Honeycomb, if you try and put a div inside a span, which is in contravention of the HTML5 spec, that will be a failure. You can't put a TD inside a div. This will also be a compile error. I'm pushing from runtime, or not even runtime, from display time in browser terms, errors up to compile time. I've said this before, but the very best time to encounter an error is compile time, not at runtime. So Honeycomb encodes all of the rules of the HTML5 spec so that when you write the code, like this here, it will convert to compile errors any mistakes you make in nesting. We can even support potentially typed attributes. So this CSS type that maybe becomes available through Contextual, we could ensure that style attributes only allow CSS types. This is an enhancement which hasn't been done yet, but it would be possible. I'm ahead of schedule. This is unexpected. Guillotine, this is maybe my favorite pun, because guillotine is for executing stuff. It's for running processes. With Guillotine, we can define a command like this. This is like Java's process architecture. We can write git commit message, and what Guillotine will do is it will treat this as a single parameter. It won't do anything stupid like just split on the spaces. It will treat this, because of the quotes, as a single parameter. It will actually parse the entire thing. That's Contextual providing that functionality. We can substitute values in. So this string here, which additionally contains spaces, that will be treated as a single parameter, which is, I think, what we would want in that case. And we can even combine the two. So we have quotes here, and we substitute into that. What this will do is it'll treat that as a single parameter. we get a compile error when we write something like this. This fails at compile time, not at runtime. It says that this, or this quote here, is not closed. So, because we've carelessly included that quote there. That's the sort of error you might actually catch using Guillotine. So that defines them. It doesn't actually run anything. When we run it, we can call .exec. That will run it using an environment, an implicit environment that either brings all your environment variables from your existing scope and passes them through to the subprocess, or you can create a completely empty environment. I haven't shown that, but that's what happens. If the result comes out as a string, we can ask for a string back. If it's something which we know will return an integer, then we can ask for an integer back. We can also get streams and other types that make sense for dealing with processes. We can even start a task and leave it running. So we can create a running process. That might take a few minutes to run on a slow machine, so we don't want to block. So that will run, and then later we can actually get the value out of it. So all of that time I gained earlier, I've now used up with Guillotine. So 2 minutes on Mutatis. We're nearly at the end. Mutatis is a little bit different from the other libraries because it depends on a third-party service. It's built around the Google Cloud Platform data store, which allows us to store arbitrary data in the cloud. What Mutatis does is it gives you what I think is probably the absolute simplest ORM. Well, not ORM. It's the simplest way of serializing data to the cloud that you will probably ever see. We can define a case class. Same one I've been using more or less consistently throughout the talk. And same example, our friend Grzegorz again. And we just call .save, and it saves it to the cloud. Now this does rely on one thing. It relies on the Google API, which checks your environment variables to know that you know which cloud account you are accessing. But apart from that, and certainly if you run this on Google Cloud, that's already set up. It's already in the environment. Storing a case class to the database is as simple as calling .save on an instance of it. That works for nested types as well, more complicated things, and lists. To get the data out again, we just create a data access object and get all the values out. I'd like to add GQL support later, but that'll come at some future date. Here's a more complicated example, just showing that we can have a list. We can have references, so not storing the data in the same record on the cloud, but as a separate record which we refer to. So this is saved, and this one is saved separately, referring to the reference type here. So anybody here working with Google Cloud? AWS? More? Okay. We can make this work for AWS as well, I think. Optometry, lenses. Gabriel showed you a few examples of lenses earlier. I'm going to show you a different approach, which is maybe simpler syntax and maybe some different priorities in how things look. So we can create a structure, an ADT structure, person, company, and create instances of that. Michal Novak, made-up person, and he's working for Acme, and he's got some staff, Pavel, Przemek, and Piotr. And what we might like to do is access the CEO's name given a company. This is how you create the lens. That, I think, is the nicest lens creation syntax I've seen. So it operates on company, and we can access a value. If we apply that lens to the company we just created, that will give us the string back. And likewise, we can replace Michal with Maria, and we get back a company. So this is the syntax for doing an update. We get back the new company with that data. We can do more advanced stuff, though. The staff, maybe you noticed, was a list or a vector. And we can apply this little operator or applicator, I'm not sure what the right word is here, each, which will allow us to, for each member of staff, each element of that list, get their salary or apply to their salary, focus on their salary. So we can apply that to the Acme objects we had before, and what we get back is a vector of double. Vector comes from the type of staff. The staff was a vector of person. Double comes from salary, which is what we get by mapping over that. That's all handled automatically for you by the lens, by Optometry. I want longer on this. This one's good. If we had a bad, I'm going to go over time. If we had a bad year at Acme, we can actually update all of the salaries to 0, for example, or add 10% if we wanted to, something like that, in one go. And the syntax is really simple. If you compare this to working with copy methods on case classes, this is hundreds of times easier. Last one, Pyroclastic. Pyroclastic. I've just paused the clock because I need a breather. Pyroclastic is a way of composing repeated operations that act on workflow graphs. If that sounds a bit vague, I will just give you an example. Let's say we want to make some tea and some coffee. So let's define some fields, some references that will store the various objects we're going to work with. We're going to need milk. We'll have some hot water, cold water, kettle, tea bag, ground coffee, and the actual cup of coffee. Having defined those fields, we can define how we fill them. So to get a kettle, I'm not going to explain the detail of how you get a kettle. We're just going to construct a new kettle. We're going to construct some new water, which has the temperature or heat false. We're going to grind some coffee and get some coffee. Nothing here is very exciting. This is where it gets interesting. To boil some water, I need cold water and a kettle. Those are prerequisites. So given those, I can propagate hot water. And the way I'm going to do that is I'm going to call coldwater.boil. You'll notice that these are references to those field types. That's a reference to the field type as well, but we're going to apply it. That application only works in the body of this method. We boil it, we get back this will actually give back a try of water, hopefully hot water. Pouring tea requires milk, hot water, and a tea bag. Same thing, we're going to propagate tea from that. That's the method we call. It returns some monadically wrapped version of a cup of tea. More or less the same for coffee. We're only allowed to apply these parentheses here to something that we have declared as being required. If we try and access the value from, say, cold water in here, then that will not work because we haven't declared it. And the types of these values here encode all of the detail of the requirements and what will be produced. This is some very extensive type system work here. Now, this is where we bring it all together. We can define preparation as composing together, getting the kettle, getting the water, buying the milk, and boiling the water. We've now redefined a new task here from these 4 tasks. These can only be defined if each one of these has all of the prerequisites it asked for in advance. If it doesn't, then we can't do it. We can make the tea by using that same preparation we defined here in both making the tea here and making the coffee here. We have reuse. We're not repeating ourselves. We're not having to define this multiple times. We just define things that are different for each case. So if you're combining tasks like this and you have sort of composable workflows with which can be represented by a graph of dependencies, then this Pyroclastic will potentially help you. To get the value out at the end, we just access T. We can access any value, but we're going to access the T from make T. Likewise, coffee. The type we get back is try, and it's all monadic. So within here, it will apply some number of times the monadic sequence and flat map as necessary to get a result. And it works for any monad, thanks to Mercato. That's all I've got on Pyroclastic. I'm going to mention some other libraries. I said I could have probably done more than 11, but my stamina for speaking at this pace is coming to an end. Magnolia probably will fill a whole talk on another occasion. Xylophone does XML. Anesthesia is something I'm working on for painless error handling. Dissonance, comparing ADT instances. Eucalyptus for logging. Impromptu for quite similar to Pyroclastic, but maybe a little simpler. Inflection, reading and writing data. Exoskeleton for shells. Get it? An escritoire is a French writing table, which is for writing tables. So, I think I'm almost within time, believe it or not. Hopefully you've seen something here that was interesting, or maybe you think applies to a task you're doing. If you have, I'm really glad. I hope you'll look at the projects and explore them some more. Just to reiterate, they are small, they are tiny, they don't pull in lots of dependencies. I think at most any one of these will pull in one or two of the others. They should be a lightweight addition. They won't conflict with anything else that's on your software stack. And maybe the most important point, all of these can benefit from your input. I build them for my own purposes, but I want them to be generally useful, and I want people to tell me if I'm not supporting something that you want to see. And I would love you to contribute, and I will help you get PRs across the line. I'm working at the moment with Virtus Lab in Krakow. They're also helping me to work with these libraries. And what I'd like to do is make these useful, well-documented, production quality, and ready for anybody to include in your application. And that's all I've got. Dziękuję bardzo.